I think,
Sorry,
ma'am.
very sorry for being late. Yes.
Yeah, that's fine. That's fine.
Yep.
So, I think today is the last session from your end on this topic of post-quantum cryptography. If I'm not wrong, is that correct, ma'am?
Yes. Yes, sir.
Yeah. Yeah. So, ma'am, the participant count has already been reached up to 200, and it's continuously growing up. So, I think we can start the session from here onwards.
Yep. Yep.
And
Sure, sir.
yeah, so it's completely over to you, ma'am.
Thank you so much. Yeah.
Yeah, ma'am, welcome for the last lecture. I think today your last lecture, na ma'am? Post
Yes, sir.
quantum.
Yes, sir. Yes, sir.
Thank you so much for joining, and yeah, over to ma'am.
Yes. First of all, to all the participants, sorry for being late. And secondly, without any further delay, let me start. So, yesterday was the first class for quantum cryptography, and we just covered the classical cryptography in a detailed way. We have seen the asymmetric and the symmetric key cryptography and covered the basis of why do we need quantum cryptography. What are the possible solutions to mitigate the quantum threats that can come to classical cryptography? As well as we have seen that what are the two different solutions or two different genres of solutions that we have to cover. Where the first one was the quantum resistant cryptography and the second one was the quantum cryptography. We primarily have seen the second part yesterday, which is the quantum cryptography, which follows the quantum mechanical postulates itself to mitigate the challenges posed by quantum computing. And today we will be covering that part. We started just the BB84 protocol. So today we will cover that part. Along with that, I will give you a sense of, because this topic was like requested by a few participants. So I will cover the essence of B92 as well as the E91 protocol. Post that, I will start with the what is PQC, which is the first variant, that what is the classical solutions, where I will cover primarily what are the challenges and what are the different variants that we have in PQC. And of course, what are the security, like how easy it is to mitigate from the quantum to classical one. Sorry, not the quantum to classical, rather all these kind of variants like classical, existing classical to the new classical, then existing classical to the new quantum. Then if possible, that can we really rely on some hybrid solutions or not? So we will be talking about all those stuffs. So let me start. So we covered the BB84 protocol, which is a Bennett and Brassard in 1984 that discovered this protocol. But we have seen that we primarily rely on four bases. Okay, one is the horizontal vertical basis as well as the diagonal basis, where diagonal can be either plus 45 and minus 45 or plus 135 degree. We have covered that part. So it was something like this. So say Alice wants to send the bit stream 1001100, that is 8-bit stream to Bob. So initially the process was Alice will be chosen a coin. Only one thing was common, that whatever convention Alice will be choosing for, like if head then the horizontal vertical basis, or if tail then the horizontal vertical basis, anything Alice can choose, but that choice should be consistent with the convention followed by Bob as well. That was the only thing. So Alice will be choosing a coin out of the random coin toss. So maybe the outcome is head, tail, head, something like that. As you can see, this is just because of a random coin toss. So Alice will be then choose the basis based on this horizontal, based on this head and tail. So head, then horizontal vertical, tail, then diagonal. Likewise, you can see for every head there is an horizontal vertical, for every tail there is a diagonal basis that has been chosen. Right. Now after that, Bob will also be like tossing a coin. Okay, and this tossing coin is a complete independent event than Alice tossing a coin. Screen not visible? Is it visible to others? Okay, please rejoin. Please rejoin. Okay, yeah. So Bob tossing a coin. So this is like, say, when Bob tosses a coin, this is the outcome. Any outcome can happen, considering the coin is a unbiased coin and head and tail both are equiprobable. Okay, come back. Come back to the discussion. Yes. So Bob tossing a coin, it is like, say, head, head, tail, tail, head, tail, kind of this. Okay. Then the basis chosen by Bob will be nothing but this thing based on horizontal. It is a horizontal, vertical, diagonal, diagonal, horizontal, vertical, diagonal, horizontal, vertical, and diagonal. Okay. So bit received by Bob was something like that. So in these cases, these cases, Alice's and Bob's basis mismatch. So there can be a probabilistic outcome. But these are all the definite outcome that Bob is getting. So 1000 was a perfect match. Right? And rest, anything can happen depending on the basis. So if anyway it is allowed that 50% of the bits will be bypassed anyway, so there will be some outcome, otherwise there will not be any outcome. So randomly, say for example, that Bob receives for these mismatched cases as well, that Bob received this particular outcome, say 1010. An initial bit stream was 100110000. So this was the original one or the intended one to be received by Bob from Alice, and this is what Bob actually receives from Alice. And all these four outcomes where both of their bases mismatch, I'm assuming that probabilistically these are the values that Bob is receiving. So if I do a match, then 1 and this 0 is a clear mismatch, and even this outcomes is a match. So these are called probabilistically correct. Rest are definitely correct solution. 2 are definitely incorrect solution, and 2 is probabilistically correct solution. So the thing is, assuming large number of bits sent by Alice, and Alice doing a random experiment of tossing a coin, there is half of the time Alice will be choosing a horizontal vertical basis, and half of the time Alice will be relying on a diagonal basis. And assuming there is a no eavesdropper, till now we are considering the situation for a not in or in absence of a eavesdropper. Okay, kind of that in the scenario. Hence, half of the time Bob's basis will be same as Alice's basis. So some bit received in 50% of the time as sent. In another 50% cases where both of their bases mismatch, consider this thing, then also probabilistically out of those 50%, again for 50% cases, they might agree. So definite agree is 50%, probabilistic agree is another, like out of the 50%, there is a 50% chance. So that means ultimately it will be same for 75% of the time. Therefore, the agreement between bits sent by Alice as well as the bits received by Bob is as much as 75%. Though Alice and Bob will agree 75% of the time, only for 50% of the time they have used the same basis. So Alice uses classical challenge to announce it, and Bob will discard those wherever there is a disagree. Followed by that, they will be checking the left out bits. Okay. So after bit transmission, Alice will announce her chosen basis in sequence. So Alice will be announcing this, means this information will be sent in public from Alice to Bob, not the bits that Alice has sent. That is what was 100 or 0110 10011, something like that for a 8 bits information, say that will not be sent from Alice to Bob. Rather, Alice will be announcing in public the basis chosen by her side to Bob, and she will make that one as a public announcement. Okay. Now, Bob removes all those bits where Alice's basis and his chosen basis do not agree, right? To maintain. Then what that means that whenever this is received by Bob, so Bob will again do his set of like bits that she has chosen and this one. And accordingly, he will be getting another set of mismatch and match. And he already has one set of mismatch and match. So he will simply be comparing them. And wherever he will see that their chosen bases do not agree, he will directly be discarding that. So to maintain uniformity, Bob will agree upon only for those 50% of the time where both of their bases, Alice's and Bob's, are same. And for remaining 50% of the time, he is simply discarding or not even considering the probabilistically correct outcome. So though for 75% of the cases where 75% is comprising of 50% of the definite outcome and 25% are probabilistically yes outcome, Alice will or Bob will ultimately for their t distribution, they will be not relying on the probabilistic outcome. They will only rely on the 50% of the time where it is the definite outcome where both of their bases are same or chosen basis is same. So that means Alice and Bob both will be choosing the right basis is nothing but this thing because if it's not present, so probability that vertical or probability of a diagonal that will be 1/4 out of the 4 bases only one will be chosen. So that means that the total probability of getting right, let me write here, will be 1 because Alice will be starting it. So for his case, it is always, for her case, it is always 1 into this thing that whenever 50% of the time, say probabilistically, Bob will be choosing the same basis as Alice will be choosing. So it's half, that is 50%. So out of 4 bases, they will be choosing the right basis that has a 1/4 of the probability, but the total probability of getting right solution, considering the situation where Eve is not present, will be 1 because for Alice it is the initial starting point, so it's always 1 into Bob will be starting, so that is half. So half of the time Bob will be dependent on the choices made by Alice. So it's 1 into half, that is equals to 50%. Right? So the structure of this is something like this. Now say for example, the next case where Eve is present. So based on the situation when Eve is present, accordingly, the rest of the BB84 has been set up. So say the similar kind of scenario is there where Alice is definitely there because Alice is the intended sender. So Alice is something like this. So say 100110000. I'm getting the same thing that Alice wanted to send. The same bit stream I have chosen. So basis was something like this. So say plus, then diagonal, horizontal, vertical. This basis is diagonal, say, and this is say plus, this is plus, this is this thing. How this is getting, I'm getting this one because I'm assuming that through head and tail. So Alice tosses a coin. And according to the outcome of the coin toss, this is the actual bit stream, okay? This is the actual bit stream. This is not used for encoding. That is to be sent. Now Alice is tossing a coin, and according to the toss outcome, she is setting up the bases. Okay. See, Eve is somewhere here. So Eve is somewhere here. Where Eve will also do exactly the same thing like Bob. I will write the Bob's outcome as well. But before that, because if right now for man in the middle attack, what is the scenario? That scenario is someone who is not the intended receiver trying to be perceived by the sender in a way that he is the intended receiver. Okay, so kind of a masking that he wants to adopt. So Eve is doing the same thing, and Eve also will be doing exactly the similar kind of a thing that Bob is doing or Bob was doing earlier. So Eve will also like toss a coin, and according to that, now only thing is that Eve will not be having that information that what was the encoding style used yet. Okay. Say, for example, this is what Eve's outcome is. Okay. And what was Bob's scenario? Let me take the same thing, same outcome of the coin toss, that random outcome of the coin toss that Bob had through tossing a coin. So it is something like this. Remember, coin toss has nothing to do, or it is absolutely an independent process about the bit stream that was supposed to be sent, or which is used for actual key generation or quantum key generation. So this was Bob's outcome. Okay, now you can imagine that here, say, say for example, for this particular value, these are all the polarization filter have the same basis, right? So definitely one will be coming. So there will be no blockage of the information one. Why? Because all of three bases agree, or say same polarization vector. Here it is a mismatch. So here it will be, because it was a match till this part. It was not a match. It was also not a match. Okay, here it's a match. So 0 will be coming here. It's a mismatch here. Again, it's a mismatch. Till this part is a match, but here it's a mismatch. So if I want to write here, it will be 1, then nothing here, then 0, then nothing here, then 1, then 0. Then in this particular scenario, I will not receive anything, right? So definitely when all the three bases agree, that light will pass through all the filters and ultimately it will be visible. So 1 and 0 definitely is here. But for the rest of the values, say here I received a 0. Here I received a 1. Here I received a, here I received a 0. And here I received a 0. So if you notice very carefully, out of these values, these two are the values. These two are the values where it is 0 and I'm getting a 0 as well. Okay. So the probabilistic correct outcome is actually true as the correct outcome if it would pass. And the rest of the values where I'm getting this thing, what are the rest of the values where there is a mismatch? Okay. Say here I am getting a 0 for the sake of the calculation. Say I'm getting a 0. So for these values, for the other values, say this is a 0, okay, no issue. But for this value, I should be getting a 1, but I'm getting a 0. So this is a case where I'm getting a mismatch. As well as it is in this thing. Say here also it was, okay. So in this scenario, so this was a 0, though there is a mismatch, I'm getting a 0. I'm just roughly considering a scenario, nothing else. So this is a 0 where I'm getting a 0. This is a 0 and 0 where in all these cases I'm getting 3 zeros. But this is one scenario where it was 1 and the bases mismatch, but still I'm getting a 0. So there can be a mix of, for this scenario, as I've drawn, so there can be a mix of some probabilistic correct as well as the probabilistically incorrect solution. But again, here also, even after that, roughly it will be some scenario where it can be like 50% of the cases as probabilistically correct and 50% of the cases as probabilistically incorrect, and 50% and the remaining 50%, which was the actual one from out of the 100%, was a definite correct. But at the output for Bob, if I see, only 2 was definite correct solution, and rest is, say for example, I'm getting this thing, so 0, here also 0 0, and here I am getting 1 1 1. So for the cases where bits mismatch even with Eve and Bob, it can be again some different outcome. So that clearly means one thing, that is, there is a dependency between what Bob will achieve with that of what Alice actually sends, and both the things are dependent on somewhere with Eve or what Eve is receiving, because Eve is the man in the middle currently. So if Eve somehow creates a kind of a blockage of the light or the like polarization bases or polarization vectors to be passing through the filter, then it will be a real challenge. So the thing is that all the remaining ones are random bits and only 2 are probabilistically correct or a definite correct, as well as probabilistically correct as well as definite correct bits. That means in presence of if, the scenario is something like this. So vertical or horizontal is equals to the diagonal, and it is equals to, like, say, half into half into half, that is equals to 1/8. This is the first thing. And Alice will be choosing with, is it any dependent one? No. So with probability, which is 100% thing I'm allowing because Alice is the sender. So this is 100%. Now Bob's chosen base series. will match with Alice's is basically half, or that is the 50% of the time. So this is not Bob, sorry, this is Eve's, because Eve right now is sitting somewhere between Alice and Bob. So now Alice and Eve is done. So Bob's chosen basis will match with, now Bob's chosen basis, in order to make it a successful one or passing through till Bob's level, it has to ultimately agreed by both the chosen basis of Alice as well as with that of Eve. So that means Bob chosen basis, if Eve is the man in the middle, has to be dependent with both Alice's as well as Eve's. Right? So it will be, that means this half into, or 1 into half in easy words. So 1/4. That is 25%. Now, what is the interpretation of this thing? That means 25% of the time only are those cases where it can yield to some successful outcome if and only if Eve is present in the scenario. So that means if I have to get, or if I say give n number of bits, only for n by 4th number of times, it will be hitting to a success. So if I have to hit 100% success in the bit received, then how many bits I have to send as a sender? How many bits? If n bits are ultimately giving me n by 4th success rate, if I want to get the n full success rate, yes, so it has to be 4n. Absolutely. Because ultimately, out of all the foreign number of bits sent, some might be lost because of the intrusion of the Eve. Okay. So then it comes the protocol, or the BBT4 protocol steps, you can say. So steps that you should be following is this, that first you should be starting with as an Alice in order to create some quantum key with you and Bob. You should be doing first step, that is choosing 4n, and still along with that, because in networking also we rely on some parity bits. So here also I will be relying on some parity bits, because why? Because ultimately 4n will be reduced to n. So at least some additional bits I should be having in order to get rid of any emergency situation or any kind of error that can happen because of the side channel error or anything, some hardware error, anything. So some additional bits I have to keep as parity. So these many number of bits to encode, and encodes randomly all these bits and sends it to Bob. So sends it to Bob. This is the first step. Second is, Bob also measures them with or using, say, random basis. The game is still not over. It's not about only sending. There are further steps. I'm coming to that. So this is at least the minimum criteria. See, all of these measures we are following, even though we are relying on quantum mechanical postulates, we rely on the no cloning theorem as well as the all the kind of teleportation theory where we are lying no sort of cloning. Measurement will ultimately, tampering of quantum state will ultimately destroy its quantum property. With all these things, still we are taking these additional measures. Okay, so Bob also measured them with randomness. Third one is Alice Alice and Bob do not know that if there is Eve or not, so he will be for safe side. She will actually set all the foreign plus delta number of bits. So third step is Alice announces over public channel. Just after sending, Alice will announce all the bases chosen. Which is a sequence of bases. Like say this. Anything it can be, okay? So something like that, Alice will be sending. But no information about the actual bits will be announced. Okay. Fourth one is, in all likelihood or in all possibilities, at least in 2n cases, their bases would agree, considering where Eve is not there, and extra delta bits taken to compensate for the possibility of actual agreement, and which can be less than 50%. So it's in all likelihood. And extra, but in worst case, it is in foreign cases, okay? And extra delta bits taken to compensate for the possibility of actual agreement. Now, fifth step is Bob will discard all those cases where the bases disagreed with his chosen basis. Bob also, at his end, done some sort of like coin toss and accordingly chosen some basis. So the cases where, so Bob will discard all those where his chosen basis. Of course, qubits will be lost. That's why we are taking 4n as well as delta. What's my original target? To only send n bits. For that, say I want to send 25 bits through that. So that means at least 120 or 130 bits I will be using. 100 bit will cater the requirement for 25, and some additional 20-30 bits I will be keeping only for the parity things if it is lost. So just to cover those kind of like hazardous situations. Okay. So my main target, the cream of the picture is that I want to send only 25 bits. Okay. So Bob will be discussing all those cases where his chosen basis will disagree. Now your question was if in these cases my actual qubits also gets lost somewhere. So in that case, ultimately, through I will cover the rest of the steps. Ultimately, if that happens, they will be sharing some further information as well. So in that case, they will simply discard it and set up a different or a fresh kind of a connection. I will come to that one. See, as a sender and receiver, the main target is I should be absolutely safe that nothing confidential information should be shared with both. Till this point, Bob will simply discard. There are further steps. I'm coming to that point. Because it's not even the key that you are thinking that, okay, maybe that is something of the actual key that is being discarded. It's again some way encoded into the bits that I'm sending. I'll come to that part. So this is the fifth one. Next step is Alice now will choose a random n bits and publicly announces the actual bits and locations. What do I mean by that? So Alice will be sending, okay, hi Bob, I have received the 7th bit, which was 0. My 13th bit is 1. My 15th bit is 1. And my 23rd bit is, say, 0. So that's how some abrupt bit positions will be shared to Bob, without any guarantee that whether the 7, 14, 15, and 23rd are even the positions where actual bits are sent or some parity bits are sent. That is not even shared by Alice yet. Okay, but some information will definitely be shared. So that means sixth step is Alice will now allow, or Alice will now say choose a random n bits. They need not to be like consecutive n bits. They can be any n bits, and publicly announces those things or those bits which are actual bits to work. So that means if we'll also have this access to this information, okay, because it's a public announcement, and Bob checks and if there exists any discrepancy, and that is a very large discrepancy, large or small, that depends on the communication specific thing, which is already a lot before has to be shared between Alice and Bob. They has to agree that, okay, if the discrepancy is more than 60% or what it is, depending on the severity of their application. Okay, but if it is very large, then they will disengage. Why? Because that will imply that a lot of bits somehow has been tampered or modified by Eve. So they will simply disengage. But in the case where, why you are thinking that flipping the bits will work here? It's not about flipping the bits. It's not the classical one, okay? So it's just through some quantum bits, we ultimately try to map the quantum bits with some actual information, which is in classical thing only, right? Whether it's a 0 or a 1. So that quantum bits are being actually somehow changed. So that may not be directly like implied with the classical error correcting code where you just simply flip the particular classical bit, make it from 0 to 1 or 1 to 0. This is not an error correction one. This is a key transfer thing, right? Okay. So it's not about only by flipping the bit or by flipping or changing the phase. Okay. Second part is if at all the error is small, that is the discrepancy is really small, then what we will do is they will use the remaining bits as some one-time pad for secure communication. But remaining bits is still a fishy thing. I will come to that one. Okay. Why? Because before using it, With shared strings, the step number 8 is with shared strings, Alice and Bob will use something like information reconciliation. What do I mean by this step? Information reconciliation is kind of error correction process that was applied or that could be applied on keys with both Alice and Bob to ensure that they have identical keys with errors, revealing as minimum as information as possible. And this is nothing but the process of cascading, whereby they divide the entire key strings into blocks and carry out some parity checks. That is the next step. So for those blocks for which the parity does not agree, a binary search is made by subdividing the blocks and repeating the process until the location is identified. And this process has given information about the location where parity does not match to that of Eve. And then Alice will pick up the random subset of strings that she as well as Bob share, then compute its parity and asks to Bob to do the same with the bits he has, which are presumably identical because it is only assumed that at that level Alice's and Bob's bits are identical. Therefore, the parities will now become the new strings. Okay, so that is some kind of a concept. Let me write that. Just a minute. Just wait for a few seconds. Wait a minute. So the case is the information reconciliation, say IR. The step is something like this. It is to correct any differences between their keys, Alice's and Bob's, without revealing too much of information to Eve or public. So they talk publicly. The technique is something like this, that they will talk publicly. That means maybe over phone or some internet, but only publicly about the errors locations where it might be. You can do a sync between the earlier steps as well as the step number 8 where we are doing information reconciliation. So after this, they will be directly sharing some of the things. They will be talking publicly about what are the error locations where it might be, but only about the error locations, not the actual key. And this is done by, say, comparing small parts. That can happen through like dividing the bit stream into smaller blocks. That can happen. Because ultimately it will not be in real case only the 8 bits. It can be very long. So ultimately it can happen by dividing it in smaller parts and then comparing the smaller parts in two terms. First one is maybe parity bits, they will announce that, okay, we will be doing some parity checking. Okay, I want to check the 4th bit position. So this information, they will make it public, right? Or maybe some error correcting code. Okay. So this is one way of like discussing, as well as keeping the hidden thing further hidden. So a lot of information they will be sharing in public, but none of them are actual bits. They're only sharing about some dummy error locations. But since all the foreign plus delta number of bits will be sent from Alice to Bob, or intended to be sent from Alice to Bob, so if they find any discrepancy, which is very large, at any point, they will simply discard that one and start for a fresh communication. Otherwise, they will proceed. Maybe they are getting the same error bits in the same error locations that they are discussing. So that means till that part, the chances of error will be minimum. Kind of that. So this is the 8th step, and the last step after they have done this thing, comparing small bits and parity and all the codes they have discussed, that is the error locations. A few error locations they have discussed over phone or internet in public channel. Accordingly, they have done some verification that, okay, that till this, but I should not be discarding. So considering they will not discard till step number 8, step number 9 is final step that they will be doing. They will do some privacy amplification step. Some privacy amplification step. What is that? It's kind of a shrink. Its theory is let's shrink and hide the key. And why this is very important? Because in the first step, 6 or 7, already have sent some information. Then information reconciliation is further sharing of some further information, because already some valid information or the actual bit positions have may be shared with Eve, because it was already in communication between Alice and Bob. Suppose that they will be doing some information reconciliation and will be just sharing some error locations between Alice and Bob. They will be discussing it over public channel. If it is even allowed, that is still this part, the discrepancy is very, very small. So further step is, because now Eve through step number 6 or 7 and 8, 6, 7, 8 has some information about the bits or the parity bits that has been sent from Alice to Bob. Next step is to do some privacy amplification. So there they will be doing what? They will shrink it and try to hide the key. Shrinking and hiding the key means nothing but they will be simply applying some hashing technique. So it's basically the theory is, let's now shrink the key that we have thought of using some hash function. Using hash function. That means now your longer key, maybe 80 bits key, will now be reduced to say 15-bit key, or say shorter or secret key. What's our main target? To make it the F inverse really hard, and that too using quantum leap. It has to be a trapdoor function, right? So that means as longer bits will be now through some hash function will be reduced to a shorter or a secret key. So even if Eve or say intruder knew a little bit about long key, through okay, let me come to that, right? She knows almost nothing about the final short key. And that is the end of your BB84 protocol as they have thought of. Not okay. Now one has asked a question that what if like Alice and Bob is trying to send something and ultimately if somehow it will collapse the some of the real bits or actual bits, and because of Eve. Now, answer is it is okay to compromise some of the actual bits. If ultimately through their information sharing, if it happens like they're unable to detect that, then what will happen? Eventually, they will simply discard that particular communication and they will not form a quantum key out of the entirely set up communication channel. That is allowed here. We can strictly bet on that part that okay, because some of the actual bits also, maybe we have just discarded all the actual bits. In all, when we will discard them through the steps, only maybe in the cases where last we are publicly discussing something between Alice and Bob, where Eve is listening something, then it can happen. But before that, Eve already should have done some manipulation on the rest of the qubits. So somehow, whether that's the rest of the qubits which Eve has some way manipulated, if Alice and Bob agree on those not actual bits but manipulated bits over phone or over some public channels, they're discussing something about that. So that will mean if they disagree, then also Alice and Bob will both discard that communication and will try to create a fresh communication. And again, set up the same thing. So when finally, out of these trials, say 1, 2, 3, 4, 5 unsuccessful trials, maybe at sixth trial, finally it's all agreed between like if maybe not manipulating that one. So everything will be as it is and it should be, or within the acceptable threshold. Then only that communication will be treated as a successful communication and that key will be taken. I'm not, again, QKD is not giving any guarantee that in the first trial, it will lead to some successful key generation. That is not guaranteed. What we are guaranteeing here is no way or never if can actually intrude in a way where he can manipulate the qubits or maybe recreate the qubits after tampering it. That means she has the information, if has the information, then also if somehow is giving you the same basis or that same basis then reflecting to Bob, and Bob is actually thinking that okay, it's the same basis with mine and that of Alice. That is why I will be simply accepting that particular bit position where both mine as well as Alice's base agree, and let us consider to be a successful transmission. So this kind of misconception is not allowed for QKD. But there is no guarantee. Again, I'm telling there is no guarantee that or any kind of minimum number of trial thing that okay, in how many trials it should ultimately be covered. But at least for a safe side, you should be trying with 4n plus delta number of bits to start. Why delta bits? Because often qubits might also degenerate with courses of time. So there can be side channel attacks, which are very much of a hardware-oriented attack. We do not know when it will happen, but it can also happen. So that will have a logarithmic decrease in the probability of getting the correct key, as well as some other factors can happen. So that's why we will keep that additional delta bits intact, as well as we considering there is an Eve, we will be safe side. We will be covering on all the foreign bits to be transmitted from Alice to Bob. Is this okay? Anyone has any question further? You can ask. So this is the essence. Our main target is what was the challenge with classical one key distribution or key exchange protocol, Diffie-Hellman key exchange protocol, that if it is there is a man in the middle, it should be detected. But in classical, there was no provision to detect that presence. But here, ultimately, we are able to detect that presence. Is it okay till this part? Anyone wants to ask any further question on this? Is it okay? QKD, or the BB84 protocol? Thank you, Mansi. And for others, we have covered two different cases. First one was a pretty kind of a considering that nothing is wrong in this world, which is kind of naive. But the practical scenario was when there is a presence of Eve. Okay. Have you got the information reconciliation and privacy amplification step, which we are doing at last? 4 bases we are choosing, all the stuff clear, right? Okay. So on that note, let us proceed. Once we have done this thing, that BB84 protocol, there are two further like protocols why Alice and Bob communicate in public channel. Can they do it in quantum channel? They are sending the bits in quantum channel itself, but they are sharing some of the information in public channel. Why to share some irrelevant information in the like quantum channel? They are sending the actual bits there, but some information they are sending in public, which is anyway discarded. So that only information, that much of an information they are sending in a classical channel. Because setting up a quantum channel is very costly. Okay, got it. So there are two further protocols where we will not be covering the details of the working procedure as we cover the BB84 protocol. You can do it by yourself if you want. I will give you some essence of what they are and how they differ from the BB84. So they are the second and the third QKD protocol, which is B92 and E91. So this B92 protocol, it's by Charles Bennett. So Bennett and Brassard only discovered BB84 protocol in 1984. Later, they have thought of why can't we do a best effort delivery kind of version of BB84? So it's kind of will compromise with the efficiency. So it will not be as efficient as BB84, but it will be somewhat simpler than BB84. Okay, just like the difference between TCP and UDP. Now we are focusing on the simpler version. Maybe it's not that efficient as BB84, but at least simpler and easy to compute. Okay, so that is B92 protocol. B is for Bennett, and in 1992 it was discovered. So it's kind of a simplified version or simplified version of BB84. Then only 2 instead of 4, here we are relying on only 2 non-orthogonal states. That means either it can be, say, Ket0 and Ket+. We are not now relying on 4 orthogonal states, horizontal, vertical, or Ket0, Ket1, and diagonal, which is plus and minus. We are only relying on 2 orthogonal, non-orthogonal states. 0 and 1 are orthogonal, and plus and minus are orthogonal. So now we are relying on 0 and plus, or you can rely on 1 and plus, or 0 minus, or 1 and minus. But those two states should be non-orthogonal to each other. And third step is in B92, Bob measures in basis. Bob measures in a basis designed for detecting which state Alice has sent, even though two states are not perfectly distinguishable. So that means that measurement outcome can be of two types. So measurement outcome, it can be of two types. The first type is when Bob will get a definite answer. So Bob gets definite answer. And you know what's the meaning of definite answer. And second one is he gets a inconclusive result. Okay. So the advantage that B92 has, it's very simpler to be set it up because it uses only two states. Here, the concept is very less amount of randomization needed for choosing the basis, right? Third one is it is a easier hardware implementation, but definitely pros comes with some cons. The cons are it is very low in terms of efficiency. So sometimes it is of no use, but bit will be generated. Okay, but you cannot use it. And if can pretend a lost photon because inconclusive result can also be a part of the measurement outcome. So if can also pretend that okay it's a result of an inconclusive result and I am a valid receiver. So in that way, that pretension by Eve is possible with respect to a lost photon. Okay, so all these things, and then what it will result to, it will actually aid to some error, or it's kind of an intrusion at one bit position with respect to what Alice has said and what Eve actually successfully able to pretend to both Alice and Bob. Okay, so that kind of a is a pros and cons. So if I want to write it, so pros will be, let me write the pros. So it's simpler to be set up. Simpler to set up. Why? Because here we rely on two bases, not the four bases. Second one is here we are relying on less amount of randomization. Okay, less randomization needed for choosing the basis. And third one is it's an easier hardware implementation. But the cons are, first point is it's very low in terms of efficiency or eta, and sometimes not useful. That's why they are not in a very much of a limelight. Or B92 at least is not in a very limelight then, like BB84. It's still a very standard one to use BB84 and customize it according to the requirement of the security practice. Second one is if can pretend. It's a very serious one, that if can pretend a lost photon, which is a result of or the implication of inconclusive outcome by Bob. So if can actually try to manipulate Alice by saying that, okay, I'm a Bob, I'm a valid Bob, I'm a valid receiver, and only because of some inconclusive outcome, you can see my lost photon. So please do not think that I am not a valid receiver. So that kind of a pretension is possible by Eve in B92 protocol. So when we can actually rely on this B92 over BB84, if I do not have that much of a security intensive application, or I can still like want to send something in the quantum channel. Of course, you can understand that it does not really satisfy the requirement as it should. Or why we are like choosing quantum over classical, that much of a requirement is not being satisfied here. So, but it's one of the QKD protocols, which came in 1992. Okay. It's quite a simpler version or kind of a similar to TCP UDP. You can think of BB84 and B92. There is another version, another QKD protocol, which is a last kind of a QKD protocol known as ECART protocol or E91 or ECART 91 protocol. So it's the third variant of the QKD protocols. It's proposed by Arthur Eckert in 1991. And the only or the main distinguishable properties that E91 has over BB84 is it relies on entanglement properties or entangled particles for key distribution. Rather, BB84 uses something, it uses a kind of a prepare and measure technique. But here it uses the Bell equality and all those stuff, right? So it's based on the entangled particles theory. So that means E91 uses entanglement particles or entangled particles. Yeah, entangled particles for your key distribution purpose. Right? And instead of using, third one is, instead of using any randomly prepared quantum states, Alice and Bob will receive one half of the entangled pair, or say from the Bell's pair. Right? And next is then they measure the particles on and randomly chosen basis. So the main deviation from BB84 is that if Alice and Bob's measurement results violate Bell inequality, then no local hidden variable theory can explain their results. Therefore, Eve, or say no Eve, can simulate these results without being detected. That is the only deviation. So BB84 uses kind of a prepare and measure thing. First prepare the basis and then measure theory. Directly, no entangled pair. But here we are using that Alice and Bob will be sharing a part of the entangled pair. So if anyway, there is no chance that if can remain undetected if wants to do something, which is not the intended operation on the entangled pair. There is no chance of remaining undetected. Okay. So, but E91 uses concept where Alice and Bob's measurement will result in violation of Bell inequalities. Okay. Then no local hidden variable, local hidden variable theory can explain their results, which imply that no Eve can simulate these results without being detected. So detection is more easier in case of this one, E91, and also it uses some sort of entangled pair. But of course, it is very kind of difficult to compute or difficult or complex to calculate. So what are the advantages that BB84 will give me? So the advantages provided by this, sorry, not BB84, sorry, E91 over BB84. It is, first one is, it will give me some sort of device independence. That means the devices, even if they are not or they cannot be properly trusted, because we are relying on the Bell equalities, and as long as Bell equality will be violated in case of a presence of if, I will consider that my key or the quantum key that is being produced, that is safe. So first part is the device independence that E91 is bringing into picture. But BB84 does not really rely on these independence theory. It's very much dependent on the underlying device. Okay, if there is some inbuilt error in the device itself, or inbuilt biasness in the device, or say inbuilt biasness in the basis that's are being produced, because we are relying on the prepare and measure theory. So if there is a preparation contextuality, then that will imply that some of the things can be not as desired as they will appear. So that's kind of a device dependency that BB84 has, but E91 is completely device independent. Okay, that is, even if the underlying quantum device is not or cannot be or can't be, say, perfectly trusted, as long as Bell equalities are violated, when they will be violated in presence of if, the key is safe. As if's presence is guaranteed to be detected. This is the first advantage that E91 offers. The second advantage is it provides ultimate quantum security, not only through quantum no-cloning theorem, which is offered in BB84. Rather, it also uses two quantum phenomena, that is quantum entanglement as well as no-cloning. Then what is the disadvantage? Disadvantage is, or cons, whatever you say, the disadvantages of E91 is, or ECART protocol is, first one is, it requires really good entangled photon sources. But getting that technically is very challenging one. Yes, so I'm not going to much of it, but device independence is simply, see, there are a lot of stuff that you are doing here. First is you are preparing the device. Then you are setting up the device. That is, you are encoding your particular prepared states into the device. You are mapping them, right? Your 101, what, nothing like that, everything. There it's like whatever horizontal vertical basis we talked about in BB84. You are ultimately mapping everything of them into a physical quantum device. Now, often the device can be I'm not telling it is definitely, but often it can be biased or it has some sort of device error, which is a very much of a hardware-based error. That can happen. But when there is a hardware error or there is some sort of, we cannot really trust the basis that we are choosing. We are claiming it's 45%. It's a photon basis, right? But ultimately there can be some error or somehow they can really change its position or change the angle that we talked about. So in that way, some sort of error chances are still a bit high when we rely on a system which is very much of a hardware dependent, which we actually do because in BB84 we prepare the hardware in that way for quantum key distribution. So all the security and all the like if presence and all, what if there is some error is leading to something which is desirable? So that is also not required, right? No error should give you a desirable or a what you desire, that kind of a result you should be getting. Then how the error detection techniques that you are following will ultimately work? Because it's not only about the first bits that are being transmitted or the first quantum OTP or one-time pad that you want to prepare through QKD, through BB84. It will be a sequence of operations. So if your algorithm is anyway working with a hardware defect, then that can really cause some concern. That is in the case of BB84 because algorithm relies itself on the device dependence. It relies on the devices that we are using. We are assuming that the bases are actually the way that we thought they are because they're in the quantum level. So every time we might not have the exact access to that. What if they deflect some way? So that kind of something that we do not have a control about is there for the device dependence factor for BB84. Is it clear now? What do I mean by device dependency and device independence? Is it now clear? I don't remember who asked the question. Thank you. Yes, definitely. See, you need to go a lot. But at least the basic idea should be very clear to you. That the basis that you are choosing 4 bases. One, you are claiming it's perfectly horizontal, perfectly vertical. But what if it is not perfectly horizontal and vertical? Maybe it's 90% horizontal and 90% vertical. 2 different bases I'm talking about. That can also happen. So that means 100% horizontal is actually 90% horizontal and 10% vertical. So these with the successive operations might lead to some sort of biasness. That is what I'm talking about. Okay. And in reality also, QKD, these are in a lot way, these are in the experimental stage. We just have the algorithm, but they are in a lot sense, they are in experimental phase. Okay. So there are a lot of other factors like I have to make the things where the measurement that we do is not really environment dependent. Prepare and measure, na? So after preparation of the basis, we ultimately have to measure it. But maybe the measurement also is dependent on some other external factors. So it's a device dependency, both in terms of a preparation of a quantum state as well as the measuring the quantum state. Because here we are only assuming that we are measuring it in an ideal scenario, but a scenario may not be an ideal one. Maybe some quantumly, some other particles, which is a quantum level that we do not have an access about. If it is not an absolute zero pressure and temperature, they also might affect the performance of the measurement outcome. Right? But here, and also in the context of theory, that whatever we have learned, we are only assuming the ideal scenario. We are assuming that they are not being affected. So we are assuming the quantum particles when they are in a absolutely in a safe and secure place, nothing, no deflection, no error, no environmental dependency, very minimal chances of decoherence. We are assuming a lot of those physical things to be happening to be true. So that's some kind of a reliance on the quantum technology that we are keeping here. But E91 protocol itself works in a way where if there is a deflection or deviation in the entanglement outcome, so 2 Salman is having some different outcome, then we will assume that, okay, then 1 Salman and 1 is maybe another hero, not Salman, like that. So if it is an entanglement based and validation, then we are also validating not only the message or the bits are true or not, but we are also validating the user. Okay, so it's an entity authentication as well as the message authentication that we are doing. Similar to this idea, so that is a kind of a advantage of E91. Now let me come to the disadvantage of E91, which says that it really requires a good entangled photon sources. Again, that's a challenge because a photon source during the entire operation need to be entangled. There should not be any decoherence or should not be any other coupling errors there. So it requires a good entangled photon sources. But that is very much of a technically challenging situation. And second one is requires very highly efficient detectors. That is, eta should be very, very high for detectors to detect and observe Bell violation. Detector also has to be in a microscopic or a quantum level. Then only it will be able to detect is there any quantum violation of the Bell's entangled state. That where the Bell entangled state is nothing but this thing, if you remember, where we do something like this, that one qubit will be shared by Alice, the first qubit say, and the second one will be by Bob, who has access of a second qubit. So detecting if there is any validation here also needs to be very highly efficient detector. Okay. So comparative study can be something like that, that BB84, say B92 and say E91. So it's like this, that it's based on a prepare and measure theory. Prepare and measure. We rely on 4 states or 4 bases. But here it's a simplified one, B92. Here we rely on 2 bases with a lot of compromise that we have to do. And E91 is mostly based on the entanglement based. It's not a prepare and measure based. Entanglement based setup or QKD. And it's kind of a BB84. It's a good start, but it's complex and hardware dependent as well as there are trust assumptions. Because it's hardware dependent, so we're just assuming that the sources can be trusted. So trust assumptions are there, but it's a very simpler one, but inefficient one. And yes, that's it. But of course, fast or easy to implement. Third one is a strongest security. It's a full-fledged quantum security that you are getting, but there exist hardware challenges. Or say quantumly some challenge. Quantumly some hardware challenges here. Also those who ask that why we are not why in BBT4 when we are sending something between Alice and Bob, the error informations and all, why we are really relying on a public channel. So see, at least with some inefficiency in BBT4, at least we can rely on some public channel, which is a classical channel. To send that, okay, my 7th, 13th or 7th, 14th, 15th and 23rd bit position is erroneous. Or please check the errors, or please check the bit positions that you have in 7th, 14th, 15th and 23rd. But in E91, the preparation is quantum, the measurement in quantum, and even the detection that whether there is any error or not, that also is in quantum level. Everything is mostly quantum, so it's offering the strongest security. But definitely, as more we rely on the quantum, it's costly as well as difficult to implement and difficult to migrate. Both, right? And that's kind of a end to our QKD situation. Anyone has any doubt in the basic context as well as QKD, whatever we discussed on both last day, yesterday, as well as today, till this part? That we use photons. This is mostly based on photon. So it's purely the photonic architecture that we use for QK. So for every discussion is based on the photonic or linear photonics kind of that kind of a physical machine descriptions we are using. It's not based on the superconducting qubits or some other qubits. Quantum cryptography fully relies on the photonic architecture that we have. And we very believe that photon is the only quantum source that we are using. Any other question? Anything else? Is it absolutely clear? Have you got the basic idea after which you can go and study the literature for the quantum cryptography? Perfect. Classical cryptography, why do we need it? Everything is clear, right? Okay. Okay. What's the time now? To set up QKD, what we need? Software and hardware. Can you explain? Software, I already have said to you, there are a lot of QKD providers. Better is to search for them. There are a lot of things like the photon splitter, how to get the like polarizer, photon polarizer, field polarizing filter. There are specific QKD providers. Okay, there's those who provide the services for QKD, both for the software as well as the hardware. There is nothing at the software level because QKD is mostly on the hardware part. Okay. So there are providers. For I can tell you two providers. One is you can check what they are offering. One is IDQ, ID Quantic. You can check there. Toshiba is also providing some solution for QKD. You can check that. I will discuss a bit more on quantum cryptography. Let me first discuss that. Can anyone tell what's the time now? What's the time now? It's 3:35. Okay. I'll discuss a bit on this one. Then I'll give some break. Let me first discuss this one. Then I will give maybe 2 to 3 minutes of break to all of you before starting the PQC. Okay. And okay, as I mentioned that IDQ and Toshiba, there are QNew Labs also, which is a Indian startup. Now they are doing pretty well. So you can also check for what are the solutions for the quantum cryptography that they are providing. Let me write here itself. Those who are unable to maybe know what it is. So it's ID Quantic or IDQ. You can check their solution. Second is Toshiba, as I mentioned, their QKD solutions. Third one is QNew Labs. Okay. You can check for these three providers. They are mostly providing services based on the quantum cryptography. Okay. Not on the post-quantum cryptography, mostly on the quantum cryptography. And quantum cryptography, as I started yesterday, it's very much of something dependent on the hardware part of the quantum, where we rely itself on the quantum particles or quantum leap. So you can imagine that there are a lot of limitations. QKD right now, there is a distance limitation that till what point I can communicate, how efficient my photon source should be, how efficient my photon detector should be. A lot of such challenges are there. So these are a very specific field study that you can do if you want. So you have to really go through their manuals and check that what are the like specifications, which specifications are better than the others. So that kind of a comparative study you can definitely do. It's not only about space, it's about a lot of other stuff because it's so much of a quantum hardware oriented stuff. Okay, there is another hardware oriented feature which comes under quantum cryptography. So first one we covered. So till now we covered this part. So quantum cryptography, we covered this thing which is like quantum key distribution, which is mostly the hardware dependent thing. Hardware not dependent, I should be writing based. Hardware based. Okay. Another one is a QRNG. And okay, in QKD we have seen the BB84. Then we have seen B92 as well as the ICART 91 protocol, all these three protocols and what are their comparisons, when to use what. I've seen that. Another one is a quantum random number generator. Now again, here we primarily mean the optical QRNGs. That is optical, that is photon-based quantum random number generators. So there are a lot of stuff similar to QKT. There are a lot of such stuffs for QRNG as well. It can be device dependent QRNG. It can be device independent QRNG. It can be optical. It can be non-optical. It can be based on some other features for quantum, not the optical sources. All these things can happen. But primarily, if I have to say, you can divide it in the way that it's a hardware-based QRNG, hardware QRNG, as well as a cloud-based QRNG solutions. Hardware-based QRNG again is a simple one. You use some sort of photon, say it's a photon with a 0 or 1, something like that. Now, when you measure it, so the field one is say 1 and the other one is 0. So when you measure it, either you can get a 0 or you can get a 1. And likewise, you keep on like measuring them, whether it's a 0 or 1, 0 or 1, 0 or 1. So only one outcome can happen, say maybe 1, 0, 0, 1, 1, something like that. And in that way, through a photon source, you can actually prepare this thing, right? Second one is cloud-based QRNG, where you believe that you are not relying on any hardware source directly. There is a hardware definitely at the back end, but you are accessing it. So it's access through cloud-based concept. It's access through cloud-based concept. And if you check for ID Quantic, I remember there is a 4 Mbps speed type QRNG. There is a 16 Mbps. There is even more, I guess 200 or something, or more than 100 Mbps source type QRNG. So when to use what? That depends on what type of application you are using. The applications where you just want to give a demo, you can rely on 4 Mbps or even a like a strong demo kind of one, or some maybe integrated application you are building where you want to show some more speed, then you will be using 16 Mbps one. And if there is a really like GTM or go to market kind of an applications where you want some very high speed QRNG, will be relying on the more than 100 Mbps, which is 200 or something. Just check what is the current specification, or at least more than 100 Mbps kind of QRNG. Simple. But for cloud-based QRNG, the main criteria is you will be accessing it through cloud. So it's kind of something where there will be some hardware. So I'm just giving you something. Say for example, you are using some qubit is there. Okay. So some qubit in the, it is there Q0. Okay. Then I'm applying an Hadamard on 0. 0 is a qubit 0. So it's an initialization thing, and so it's an initialization, initializing qubit with K0, right? Then you are doing an Hadamard on that. So it will give you a K0 plus K1 by root over of 2, right? Then you are simply measuring 0. Then what it will give you? 0 or 1, right? Now say you are applying this thing a lot many times. There is a loop. Say for 10 million times you are doing exactly the same operation and you are generating some random bits. You are using some quantum random source or quantum source for generating the bits. Now can you imagine, or can you just refer or identify that how and why we are using quantum randomness for building our quantum random number generators? right? So it's random number generator or any form of random source that you want to rely on. Maybe it's a bit of tangent for a few of you. So it's a pseudo random number generator that we do using our Python function, maybe, or the way we code it. So through code or through some math function, we can only generate some sort of pseudo random numbers. And the most powerful one is the Marcin twister. Marcin twister TRNG. Okay, it has certain period of 2 to the power 19,000 something. So XYZ I'm writing. So it's a very high periodic kind of a function that we use. And this is so high that detecting that whether there is a period. Periods means after a certain period, there are generally some repetition in the random numbers, which is of course not a very desirable one, because we want perfectly random. Because perfectly random scenario gives us a lot of information about nature. It shows us that it will be a completely unbiased situation. So in cases of sampling, we can use it. In some other applications also, we can rely on that. But if it is after some repetition, say for some sine curve, so after this 2 pi, there is a repetition. So period of sine function or sinusoidal curve is only 2 pi. But what we need a very high period so that it's impossible to be done. Or rather, the best desire here is not to even have some period. There should be no repetition. But with a mathematical model, it's not possible. So here we rely on the classical computers to create these kind of random number generators. And the most powerful version that we use is the Marcin twister. It has a very, very high frequency. But again, since theoretically we aim for some, when quantum arrive, we theoretically aim for some quantum solution. So we thought of what can we do with the next version. So next version is the true RNG, or it's also known as HRNG or hardware-based RNG. Where we rely on what? We rely that if it is very random source, the source itself is very random. Maybe say sea wave noise, or say some traffic noise, where there is almost negligible pattern. If we use that source in order to derive our randomness or entropy. Entropy is a measure of randomness. Okay. Then we relied on. But only thing is that these are all classical sources. They are not quantum. They are classical, but they are not really mathematical. They are rather classical physics based. Only one difference is, only one say disadvantage or difference with this one with the quantum one is, here, since it is classical, means it's something where we can enter into the macroscopic world. It's macroscopic, right? So there is a possibility of some tampering or manipulation of the classical source. So there exists a chance of tampering the source, just like in the Sholay movie. Okay, it was a both side head. So in classical, if it happens, then we have the possibility because it's a macroscopic world. Macroscopic calculation. The next one was, we will use a random source. Everything was there, but that random source, instead of a classical random source, now it will be a quantum random source. That means it will be nothing but a quantum computer. And the random number generated by this are mostly based on quantum physics, and they are called quantum bits. Why not quantum random bits? Because quantum and random, they are they can be interchangeably used. Quantum is nothing but random. So instead of only classical random bits, it's okay. But quantum random bits is a wrong thing because quantum itself is random. So here we will be relying on the quantum bits. So now our operations like setting a something with 0, then Hadamard on 0, then third one is the measurement on 0. Now you realize, now you can think of if I apply a for loop, say for 1, 2, say 1000, then at least 1000 quantum bits we can generate. Right? And these are the essence of quantum random number generation. Clear to all of you? Till this part is clear? Great. Okay. How many more pages I have? Only one page. Ignore. So no cloning theorem. Now you got the full idea of quantum cryptography. I can say that. And only the remaining side I will cover it on the other vertical, which was a post-quantum cryptography. Right? So no cloning theorem, you know this once. I'll not get into much of it, but we cannot really clone something. It's why I have added this one because it's very much of a dependent with the BB84 and all the quantum cryptography stuff. Intrusion detection, and you know that how to detect the presence of Eve and what are the measures that they choose. Okay, Alice and Bob both, which was a quantum stuff on the first hand. Second is information reconciliation. On the third phase, it was privacy amplification. And in all these terms, we can actually measure the detect the presence of Eve. So now is again we now have covered this entire part. Okay, now we are here, which was, if you remember yesterday's class, there was an alternative solution to tackle the quantum threats that can happen through the evolution of quantum computers, which was because of like Shor's and Grover's, which was divided or subdivided into the category or the world of quantum resistant cryptography or quantum safe cryptography or quantum resilient cryptography, alternatively known as PQC or post quantum cryptography. Now here what you can expect from me is, from PQC, is to give you the initial idea, to actually to tell you or to familiarize you with the different PQC algorithms that we have and what are the challenges and what currently industries are expecting out of the entire, all these two verticals together. Okay, I will try to discuss something on that. I will skip one part, that is the intense maths of PQC. It's so huge that only PQC has 5 verticals. So each vertical with at least telling you the entire math is so huge that it is going to take 10 hours only to cover all the math part of PQC. And it will be of no use, I can understand, because it's like for the very first time you are understanding it. So if later we have any scope of introducing or doing it in a detailed way, at least for 10 hours, we can do that. But right now, I will skip that part. But I will definitely introduce you with what it is and all those initial stuffs. Okay? Got that. So, traditional cryptographic schemes deployable on classical computers, and they are known to be quantum resistant. So they are basically all these approaches are on classical. They are not quantum, nothing to do with quantum. So the classical algorithms that we had for security, like the RSA, ECC algorithms, mostly the asymmetric encryption algorithms. I already shared that asymmetric ones are really broken. They cannot be weakened. They are broken. So their severity is more. So we should be deprioritizing the symmetric ones right now more, because asymmetric ones are more severe to be under attack by quantum computers. So PQC is mostly based on the asymmetric, like variants of the asymmetric versions, right? So these are all the 5 variants. As you can see, there is a hash-based function or hash-based PQC, the code-based one. I guess something is missing here. Okay. There is a multivariate one. There is a lattice one. I guess it should be here. Super singular one is there. Okay. Somehow it's because of the, okay, yes. Okay. So it's an isogenous one. Yeah. Okay. So it's based on the Merkle signature. So, okay. Firstly, all these 5 variants are dependent on 5 different mathematical models. 5 different mathematical structures or mathematical algebraic structures. Okay. And most important ones are the lattice-based one. I will tell you why. Because there are 4 algorithms that right now has been successfully accepted. 3 are some variants of these 4 algorithms which are under discussion. So maybe 2 more or 3 more. But primarily till these 4 algorithms, it has successfully been accepted as a PQC algorithm, and they are Crystal-Kyber. And all the work that you can see for this one is by IBM. So IBM PQC. You can search it. There is a big manual or kind of a thing of a lot of pages. You can actually, if you want, you can go through that. It's still in so much of a R&D stage right now. Not even D, it's purely on the R stage, a research stage right now. Okay. So it's a Crystal-Kyber, it's a crystal dilithium. It's a Falcon, as well as it's a Sphinx Plus. These are the 4 algorithms, 4 PQC algorithms. How these 4 have been evolved, let me come to that. So lattice-based algorithm, they follow some mathematical thing like learning with error, which is based on the lattice problem. And we also use the ring learning with error, or RLWE. Okay, some advanced form of that. So it uses some kind of a lattice structure. And kind of concept is something like that. I will not get into much of it. Say, for example, I am in this position. I have asked you what is the shortest vector that matches with this particular vector. Okay. Say one easy diagram is this one. Say I'm here. Say I'm here. I have certain coordinate x1, y1. And all of them have some coordinates. This space is called a lattice. Now I have asked you that, okay, in this, from this position, which is my shortest position where I can, with a minimum distance, I can like or go to. Maybe you will say me, okay, this is the position. And now you might think that, okay, why finding this thing, which is a SVP or a shortest vector problem? Shortest vector problem is really that difficult one. I'm telling you why, because now here you are in the picture, you are only considering a 2-dimension one. Consider it in 3D, increase another dimension, then likewise consider a 100-dimensional lattice. Now, can you imagine a 100-dimensional lattice, how difficult it can be from an arbitrary point to choose that what will be your like shortest distant vertex or vector? So that kind of a structure here is used. So, and all the PQC schemes are so difficult to be done in real time that they are even safe using classical as well as in quantum. Because in why classical, of course, you know, because they are so hard that even a quantum computer cannot do that. That's the first thing. Okay. And second, so classical definitely can. And the second one is they are so hard to be encoded into a quantum computer that brute force even using these PQC or hardest of the math techniques are very, very difficult. They are not really that easy one. With a 100-dimension and with a lot of factor, it needs a very, very strong quantum computer, which we believe till it's still in the research phase. We are believing that even a very strong or a powerful quantum computer also cannot do that, because finding the quantum algorithm that would do that is very, very difficult for this type of problem. All these things are based on like quantumly hard is based on our assumptions, because we do thinking that that much of a difficult quantum algorithm that can break PQC is really not possible. But nothing is finalized yet. All these algorithms are being discovered by some researchers all over the world. They are submitting it to one actually once a portal or one hub. I will talk about that. And then they are just based on some testing they are doing, they're analyzing that how hard they are. They're trying to do some test on the attacks or some classical attacks on them. Then accordingly, a lot of algorithms they are discarding and a few they are keeping as of now, that they're thinking that they cannot be discarded, so they have selected this. Likewise, as I mentioned, these are the four algorithms that so far they have selected. And there are already 4 rounds of this kind of algorithm submission, and then testing, then validation, a lot of stuff. A lot of algorithms they have proposed which have been cancelled later. Maybe in first round they proposed, in third round someone disproved the logic and theorem, and they tested that there is an attack scenario possible. Likewise, they have been discarded. Okay. So likewise, it's a post-quantum scheme. First one is the lattice-based one. And why I told that lattice-based one is the most important one? Because the last selected algorithms like Crystal Kyber, Crystal Dilithium, and Falcon, all of them are based on only the lattice-based one. So multivariate, isogeny, and code-based ones are still in so much of an R&D one that they have not really successfully come up with some solution on these 3 verticals. These are very much of a mathematically conceptual level. They're trying to figure it out with the encryption and decryption or the security protocols. Only hash-based ones was Sphinx Plus, which is still in some way in use. So that's why they have thought that lattice-based ones are thought of to be the most kind of a suited version for the PQs so far. Okay. But these are all the verticals, 5 verticals that we have for PQs. So multivariate, so lattice, I told you, multivariate ones are mostly based on some difficulty of solving some nonlinear, usually some quadratic polynomial over a finite field. Of course, as you were like, it seems to be, it's very difficult. You know, also in ECC also, it was so difficult. So algebraic calculations and all, only to consider 2G. Now you can imagine if ECC is under threat for that. So these are mathematically very, very hard. Okay. The hardness of the system depends on the size of the finite field, variables, and degree of the system. Right? And the public key for asymmetric public key system using multivariate, the public key is a set of multivariate quadratic polynomials. And the private key is the knowledge of a trapdoor that allows solving the multivariate system. Note this level, at least. Code-based cryptography, it's based on the Macauley's public key encryption scheme that uses some error-correcting code to hide the contents of the message during transmission on an unreliable channel. So that's why it's a code-based one. So mostly we can think of that it relies on some sort of parity. A lot of parity bits in order to hide the actual information so that the inverse function remains difficult. Right? And to the message sender, deliberately adds an error, as I told you, in order to protect the contents of the message against an eavesdropper. Okay, so it's adding more error into the system so that even it is not only the case of code based, even in lattice based one, the same thing. You add as more error as possible. Now, error addition can happen through additions of some code, through addition of some erroneous polynomial. There are a lot of gibberish polynomials we are adding in order just to make the system a more complex. Similarly, we can add a lot of dimensions, which are pseudo dimensions in the lattice one. That's how we can add a lot of errors into the system. Our only purpose is the intruder will not be able to decode or decipher the actual information. Hash-based ones, okay, their idea is to use some sort of XMSS, which is an extended Merkle signature scheme. Okay, so it's a kind of a protocol where we use a kind of a tree-like structure. If you see it, if you want to go in a deep dive of hash-based one, so it uses some sort of tree-based one. And then it uses some sort of consensus that based on this and this, I have to approve this. And if this is approved, then at least the optimal substructure property type of concept, then for this calculation, I will only rely on the security provided by this node or this level. Likewise, so it uses some kind of XMSS is extended Markle, and this tree is known as Markle tree. Okay, and this concept is extended Markle signature scheme. And this is Sphinx plus the new variants of this and this considered to be quantum resistant, and that which mixes these two things, they are known as Sphinx plus. Okay. Okay, then the fifth one is super singular elliptic curve isogeny. So these are based on super singular elliptic curve. They have a similar structure to classical Diffie-Hellman and ECDH, which is elliptic curve Diffie-Hellman approaches. Right? So here the main idea of PQC is introducing error or say mathematical error through 5 ways as of now, since there are 5 articles. It can be either in lattice, it can be in the code or error correcting code, or more of the error codes we are adding or parity bits we are adding. It can be here as some of the gibberish, say some attributes that we are adding for hash based. Here we are adding it some for that one that it's a multivariate one, we are adding some sort of polynomials, which is an error polynomials, or we can add it some sort of in terms of some elliptic curve, which is a super singular elliptic curve, some error curves that we are adding. Okay. So hash-based algorithm and encryption algorithm are on a quantum thread in the post-quantum era. I will not discuss about these. These are all the classical algorithm I already discussed. So these are just the names, you can go through it. So just see, since it is Grover, so it's 2 to the power 256 has become 2 to the power 128 because it's a root n. Okay, so that means if initially it offered 256 bits of security for the symmetric ones, these are symmetric, okay? All these are symmetric mostly. So now they will offer 128 bits of security level. So that's why you can see 256 to this one. Then 384 will be half of 384, which is 192. So these are all the symmetric algorithms. Secure hash algorithm and all this. Research opportunities are, you can of course see the maximum level that you can achieve is you can develop some PQC algorithm based on any of these 5 variants, and you can actually send it to the NIST or National Institute of Standard and Testing, which actually allows for several versions of these PQC algorithm testing, and they actually submit, they accept the algorithm proposals. You can do that. That is the highest level of something that you can do. Also, you can do that, you can pick up one particular vertical and you can check that whether there are a lot of stuffs, there are a lot of challenges. I will come to that. I will come to that. Okay. So these are the PQ initiatives like PQ Crypto, Safe Crypto, Crypto Math Crest, and Post Quantum Standardization Initiative. Okay. These are all the initiative bodies that we are doing it. Okay. So PQ Crypto, it's a design a portfolio of post-quantum public key crypto system. Goal, they have set up a certain goal, have to have an increased speed, security more, adaptive to the recent applications. Right? Safe Crypto is another one, which is a secure architecture for future emerging technology. So these are all the cryptographic bodies which are now working on the PQC parts. Safe Crypto is another one, which is a secure architecture for future emerging cryptography. So their aim is to achieve a 10x speed up in throughput in real life applications and 5x reduction in energy consumption. That means at least you understand there is a speed issue here. That's why they are trying to do something with the speed, and there is a throughput issue or the kind of energy issues as well. And since we all are heading towards a green energy or the lowest energy, carbon emissions, are all the stuff. So that's why opting for an energy efficient solution is another challenge that you have a scope of research. Okay. Then cryptomath CREST is another body. It's a part of the CREST funding program run by JST or Japan Science and Technology Agency. They also have some certain goal to make it most industry savvy, to evaluate the security and efficiency, study on mathematical object and reduction map that used for by cryptography adversary. Adversary means the attacker. Okay. And exploration of the theoretical background for quantum technology and quantum information theory. And the fourth one, these are the like 4 groups, Japanese group that are working on that. You can check that. I'll share the PPT. Fourth one is the NIST ones. Okay, that's the NIST. So this is the main body which are working on this particular thing. So from they have started on 2016. We are at 2025 and the search is still on. At the end of 2024, they have successfully figured out the Kyber, dilithium, as I mentioned, dilithium, Falcon, and Sphinx. Ultimately, they have come out with these 4 solutions. Okay. Few things that you can get here, which is public key infrastructure, where the key components were certificate authority, which issues and manages the digital certificate, registration authority, which verifies the identities before issuing some certificate, public and private key, you all know what it is, and certificate revocation list, or CRLs, which maintain some invalid certificate records. So this is the PKI, and why I have separately kept a slide for this is you will be knowing this thing or getting this term very often. So it's a kind of a framework for policies, technology, procedure to create, manage, distribute, use, and store and revoke some sort of digital certificates. And this is a primary component for the PQC algorithms, the Kyber, dilithium, all those algorithms. Okay. And what are their purpose? You can also check it here. Another one is I know that. That's why I have not gone into that map part. Trust me, at least the lattice one can be covered in, I guess, at least 10 to 12 hours. And absolutely, that are so high-end maths. Again, I'm telling, if you want, you can check that it is almost impossible. And deriving everything is of no use to show you or make you go through that one. So we can do it separately if at all in any session, if that is permitted. Right now, I'm just skipping that one. So just I am telling you till that, but at least you can have a start, or you can at least think of starting with the PQC. Okay. Thank you so much. So another one that you will be getting is KEM, or key encapsulation mechanism. So KEM in very easy words, it's nothing but the simple form of an encryption and decryption thing together. So it's altogether known as the KEM, key encapsulation mechanism. There are a few terms that has been introduced, like PKI, I told you, like KEM is another one. There is a part 2 of it. Okay, just go through that. Everything is in a quantum or PQC level. So Crystal Kyber is the only algorithm out of the 4 algorithm, which is a lattice-based key encapsulation mechanism, or kind of that is Kyber is an encryption decryption algorithm, nothing else. And I prepared these things also to talk about this, like how the entire suite of Kyber works. But I know that it cannot be covered in 2 hours. Okay, so it's a standardized version by NIST. It's an accepted version, and only the Kyber out of the 4. So there is only one key encapsulation mechanism, or KEM algorithm, or the encryption decryption algorithm, which has been successfully accepted by NIST. That is a Kyber. And all the other 3 algorithms, which is dilithium, Falcon, and Sphinx, where Sphinx is the only hash-based, and Falcon and dilithium also they are lattice-based. All the 3 other algorithms are simply digital signature algorithms. Okay, none of them are based on the encryption decryption. They are simply digital signature algorithm. And for signature algorithm, I just want to touch a base of the classical signature scheme, digital signature algorithm. Not on a much of it, because the asymmetric encryption, if you recall, where there was a and there was a B, and we call that for asymmetric, it will be having a public key, a pub, and a private, So it's a 2n number of keys. Similarly, it's a B public and a B private. And it was something like that, that A was using B's public key, right? So for encrypt, A was using the data itself or the plain text and the B's public key to send it to B, and B uses the ciphertext as well. For decrypt, B uses the ciphertext and B's private key of B. So digital signature comes before that. That digital signature is mostly, why we are talking of digital signature? Because the dilithium, falcon, and sphinx, all of them are digital signature algorithms in the PQC era. I am covering this part because I have not covered, yesterday I covered only the encryption decryption one, which is the KEM one. I covered it. But I have not covered that how the digital signature works for classical. So just telling you that one. So digital signature is mostly for the non-repudiation. That is no denial. Sender cannot deny that I have not sent. Receiver neither can deny that I have not received it. So considering both of the non-denial scenario to be true, what A will do is A has to first publicly, A has to first digitally sign A's presence. And how we can do that? Using A's private key. So A will be signing it or digitally sign the data with A's private key. That is a private key of A. Then A will encrypt. So A before encryption will sign the document first. And B, after decrypting, has to also unlock this A sign with help of A's public key, right? So that means the sign has to be, B has to do that with A's public key. So public key of A. And based on whatever he is getting, B, at the end of the unlocking the digital signature done by A, then B will be checking whether that is the same as the one that B has received or not. And if they differ, that means it is some way broken. If it is same, that means B has also, B has decrypted the original text, as well as B has now the proof that A actually has sent the data. Otherwise, how it can be unlocked by A's public key? That means A definitely has signed the data using A's private key. So that's kind of a bank, what bank uses with us, any user. I think I'm already done. It's already past 4 or post 4. I'm not sure. What's the time now? I have not really got anyone, but there can be implemented one. You please check the manual that IBM is providing for the PQC one. Please go through that. There is already something that they are doing. 4:15. Oh my God. Okay. So I will, sorry for taking 15 minutes more from your time. So I will end here. I will not put much. Rest are the few things. This is just a summary part, or what are the rounds and what are the things. I already covered this one. Only a few point I want to mention. Okay, I started with even the details of this one. Okay, only a few things that you remember, that a PQC, though it sounds to be very like too good to be true, and it is actually that, even it is stronger and harder to implement than the quantum cryptography. So it only has till now it has a research potential, because full-fledged PQC ones is very difficult, because for most of the 5 out of the 5 variants, for most of the algorithms, there is a significantly increase in terms of the ciphertext and the keys that we are using. So the key overhead and the ciphertext overhead is a really challenging situation, because if I encrypt it, that's something, but ultimately I have to also decrypt it. So likewise, encryption decryption is incurring a lot of overhead, and that incurs a lot of cost as well as into the system. So it's a computational overhead. It's a lot of memory that are being used. There is a implementation hardness. A lot of such stuffs are there. So what you can think of as a researcher or as an developer is to go for, just check what are the challenges, like key and ciphertext sizes. You can see side channel attacks are possible. analysis depth, maturity and analysis depth, and most importantly, the applicability, that whether depending on IoT, blockchain applications, because everything uses a public key infrastructure or say that asymmetric key encryption. I told that blockchain also fully relies on that. IoT also relies on that. So you have to think of that how in different PQC algorithms can be mapped to those different diverse applications. Okay. And on that note, I want to end here. Thank you so much for all your patience and continuous querying and everything. Okay. Yes. Thank you. Thank you. These like last 2 days topic, even like whatever topic I cover, at least in the second part, all the last 4 days were extremely kind of a rigorous one. I accept that. Both for the complexity classes, 2 classes for complexity as well as 2 classes for cryptography. If you face any doubt, you can contact me. You can get my contact from the Dr. Pilli or Dr. Ashish. I guess they will help you. Otherwise, internet is a like vast information space. You can search there as well. Yes.
Hello, am I
No,
audible?
no, 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 no. Just one question. To breaking RSA 2048, 20 years on simulation on QC. Simulation in classical, I don't know. For quantum, it's very less. It's very less. And almost RSA 2048 going to be obsolete, I guess. It offers very less amount of security. So just like AES 128 is almost kind of broken, though it's a symmetric one, but we are not to be used in the after a few years. Likewise, RSA 2048 also we cannot use that. Yes, sir. I will end here.
Yeah, okay. So am I audible, ma'am? Yeah.
Yes, sir. Up to you.
Yeah. So, Pillai sir, are you there? I think he is in meeting or somewhere. Okay, ma'am.